आवाज येतोय का? आवाज येतोय का? हॅलो, आवाज येतोय का? आवाज येतोय का आवाज? येतोय का आवाज? हॅलो, सर ये आवाज येतोय का? आवाज
हा सर, येत आहे आवाज.
येतोय ना? ओके,
हा.
ठीक आहे, ठीक आहे.
पुरा आहेत का? किती आहेत?
पाच.
काय साडेसहा होतात काय?
आता झाली साडेसहा. आता झाली साडेसहा. आवाज येतोय का?
बाकी कुठे गेली पोरं?
आवाज येतोय का? आवाज
कसं येतोय?
येतोय ना?
बाकी
हो
कुठे
सर.
गेली पोरं?
बाकीचे कुठे आहेत? बाकीचे हॅलो, बाकीच्यांना जॉईन करायला लावा पटकन.
ते इकडचं खालचं कुठवर दिसतंय?
खालचं ते पांढरं पांढरं
इथं.
हा,
तिच्याकडे
खाली थोडं
आणि वर
वरती तुमच्या
इथपर्यंत जरा जरा वरती आता दिसतंय? खाली कुठवर गेलं बरोबर? इथपर्यंत एवढं खाली नाही. इथपर्यंत ना?
इकडं पूर्ण इकडे इकडे
इकडचं
इकडे थोडं 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 आवाज
इथं
जवळ ठेवला तर आवाज नाही. लांब ठेवला तर आवाज जात नाही.
आता वरचं सगळं दिसतंय का?
हा, वरचं सगळं दिसतं. वरचं डायरेक्ट यांच्यापासून दिसते.
किती आहे पोरं?
झाली 15.
येतात
फार मीच व्हायचं झालं सुरू
Hello, good morning to all of you. Last time we have started time independent Schrodinger wave equation. In many problems, potential is independent of time. Therefore, we have separated two separate equations. One equation contains space variables. Second equation contains time part. So these equations are derived in last lecture. Minus x cross square upon twice here. 1 upon u del square u plus v of r bar that is equal to e. That is equal to. Second equation IS cross upon p dk upon dt that is equal to constant e. Again. So So these are that is two equations. First, that is minus x cross square upon twice m 1 upon u. U is a function of only space variables x, y, z. Del square u, del square Laplacian operator plus we have r bar. Potential that is a function of only space variables x, y, z. And that is equal to some constant we have taken, that is E. It has dimensions of energy. Second equation, is cross upon t, dt upon dt equal to E. Now see that these are two separate. First that is in terms of base variables, second that is time part. Now we have to derive Schrodinger's time independent wave equation. That is also called as steady state Schrodinger wave equation, that is from equation. Therefore, multiply equation 4 by u. U that is, it is a function of x, y, z only space variables. So here let us multiply equation 4 by u. Therefore, minus x cross square upon twice m. U and 1 upon u will cancel, del square u plus v of r bar u, that is equal to or minus x cross square upon twice m del square u is a function of base variables x, y, z. That is u of r bar plus v of r bar, potential energy is a function of space variables x, y, z. U, that is function of base variables x, y, z. We have taken that is r bar, that is equal to E u of r. Now see there, minus s cross square upon twice m del square u of r bar plus v of r bar u of r bar, that is equal to E u of r. And this is nothing but Schrodinger's time independent wave equation in 3 dimensions. Minus s cross square upon twice m del square u of r bar plus v of r bar, function of only x, y, z space variable, u of r bar, that is equal to E u of r. Now rearrange this equation, that is minus s cross square upon twice m del square, if that is del square plus v of r bar, if that is common u of r bar, that is equal to E u of r minus s cross square upon twice m del square plus v of r bar, common, that is u of r bar, that is equal to E u of r. But see that this quantity minus s cross square upon twice m del square plus v of r bar, it is nothing but one operator, and that is called as Hamiltonian operator. Hamiltonian operator. In last lecture, we have discussed on the operator. Operator operates on the given wave function and produces same function multiplied by that scalar quantity. So Hamiltonian operator minus s cross square upon twice m del square plus v of r bar. This Hamiltonian operator denoted by h. That indicates operator. Yes, yeah, that is equal to minus x cross square upon twice m del square plus v of r bar Hamiltonian operator. Now see that this Hamiltonian operator operates on the function u of r bar, produces same function u of r bar multiplied by this quantity n. Now this equation can be written as x cap u of r bar that is equal to e u of 7 number equation. X cap Hamiltonian operator minus s cross square upon twice m del square plus v of r bar x cap u of r bar that is equal to e. It is Hamiltonian operator h cap. This equation is called as time independent Schrodinger wave equation in 3-dimensional case, or it is also called as steady state Schrodinger wave time independent Schrodinger wave equation is also called as steady state Schrodinger wave equation. Equation number 7 or equation number 6 is nothing but time independent Schrodinger wave equation in 3-dimensional. H cap u of r bar. Operator Hamiltonian operates on the function u of r bar. To say same function u of r bar multiplied by the distance. Now see that from equation 6 we can derive, or that is 1-dimensional case, or in 1-dimensional case. Here del square is nothing but Hamiltonian. For 1-dimensional. First thing that is minus x cross square upon twice m minus x cross square upon twice m del square Laplacian operator, that is del of 2 upon del of x plus del of 2 upon del of y square plus del of 2 upon del of z square del of 2 upon del of x square, del of 2 upon del of y square, del of 2 upon del of z square u of r bar that is equal to e u of r bar, function of that is only space variables x, y, z, minus s cross square upon twice m del square Laplacian operator, del of 2 upon del of x square plus del of 2 upon del of y square plus del of 2 upon del of z square u of r bar that is equal to e u of r bar. Three-dimensional time independent Schrodinger wave equation in 3-dimensional case, or it is also called as steady state Schrodinger wave equation. Now we have to derive this equation, or we have to, that is produce 1-dimensional case. This equation in 1-dimensional case minus x cross square upon twice m minus x cross square upon twice m. Take that into 1 dimension along x direction. Del of u upon del of x square. You are saying is a function of space variables x, y, z minus x cross square upon twice m. Del of u upon del of x square in 1 dimension, that is along x direction. plus here we have r bar plus is at plus we have r bar is equal to E of R correction minus x cross square upon twice here. We have 2u upon the above x square plus the above 2 upon the above y square plus the above 2 upon the above x square. You are common plus we have r bar potential energy that is equal to E of r bar. And in one dimensional case minus x cross square upon twice the above u upon the above x square plus potential that is we have r bar is equal to E of r. Time independent Schrodinger wave equation in one dimensional case. Now that is there in this equation minus s cross square upon twice here. The above 2u upon the above x square that is equal to E. If we have r bar on this side, E minus we have r bar u of r minus s cross square upon twice. The above 2u upon the above x square that is equal to E minus we have r bar into u. मला वाटतं पुढचं झालं असेल तुमचं आपण इथे थोडं हे करू. Or minus s cross square upon twice here. Or that is the above 2u upon the above x square that is equal to minus twice m upon x cross square. It is minus s cross square upon twice m on this side, RHS. The above 2u upon the above x square equal to minus twice m upon x cross square. E minus we have r bar into u of r. The above 2u upon the above x square that is equal to minus twice m upon x cross square into bracket E minus we have r bar into u of r. Or take this on this side, the above 2u upon the above x square plus on this side it becomes plus positive. The above 2u upon the above x square plus twice m upon x cross square. The above 2u upon the above x square plus twice m upon x cross square. E minus we have r bar into u of r bar that is equal to 0. Next number 8. Time independent Schrodinger wave equation in one dimensional case. The above 2u upon the above x square, the x direction, plus twice m upon x cross square, E minus we have r bar into u of r bar that is 0. थोड़ा अपन स्लोली इधर लेना सीखते हैं. Or the above u or dtu upon dx square. One dimension case. dtu upon dx square plus twice m upon s cross square. E minus we have r bar into u of r bar that is equal to 0. time independent Schrödinger wave equation in one-dimensional case. It is called a steady state Schrödinger wave equation in one-dimensional case. dtu upon dx square plus twice m upon s cross square into e minus v of r bar u of r bar. This equation that is very important in the for that is next chapter applications of Schrödinger's one dimension dtu upon dx square plus twice m upon s cross square the bracket e minus v of r bar u of r bar that is equal to. Now we have also derived that is second equation, that is equation number 3, that is time part. Now we will derive that is solution for time part. Solution for time part. Now that is equation number 5. IH cross upon T dt upon dt that is equal to two equations, one in space variable, second one in time part. From that is space variable equation, we have derived Schrödinger's time independent wave equation in three-dimensional case and also in one-dimensional case. From equation which contains only space variables. dtu upon dx square plus twice m upon s cross square e minus v r bar space variables x y z v of r bar. Here that dtu upon dx square along x direction take that is e minus dx only dx direction one dimension. Now solution for time for t, and for this equation consider equation number 5 is cross upon t dt upon dt that is equal to t. Rearrange this equation dt upon dt that is equal to t dt upon t equal to t upon is cross dt upon dt equal to t upon is cross into or dt upon t that is equal to dt upon t equal to is cross e upon is cross into t. dt upon t that is equal to e upon is cross into dt. Take dt on this side. dt upon t equal to I equal to e upon is cross dt. Rearrange this equation. Multiply this equation on RHS by e I and also divided by I upon I multiply. Therefore, dt upon t equal to I upon I square s cross square t. Multiplying and divided by I on RHS dt upon t is equal to IA upon I square s cross dt. But I square is nothing but I equal to under root minus I square equal to minus 1. I square that is equal to minus 1. Therefore, dt upon t that is equal to minus IE upon S cross dt upon t is equal to minus I square becomes minus 1 minus IE upon S cross into t. Take integration on both sides. Integration of 1 upon t. Integration of 1 upon t becomes log of t to the base. Integration 1 upon t dt it becomes log of t to the base e. Integration of minus I upon S cross dt. So it becomes minus IE upon S cross. Integration dt becomes log of t to the base e. Integration of dt upon t. 1 upon t integration of 1 upon t becomes log of t to the base e. That is equal to minus IA upon S cross integration of dt. But or take that is log of p to the base equal to minus I upon S cross p plus constant of integration c. Constant of integration c. Log of t to the base e is equal to minus I upon S cross p plus c. Constant. Constant of integration. See that is constant of integration. But I can see that constant of integration c is equal to 0. Constant of integration c equal to 0 when time t equal to 0. Constant of integration c that is equal to 0 when time t. Therefore, log of t to the base e equal to minus IE upon S cross e. Log of t to the base e that is equal to minus IA upon S cross into t. Remove log out log of the LHS. Remove log. Therefore, p equal to e raised to minus IE upon S cross into t. Remove log, it becomes t is equal to e raised to t is equal to e raised to minus I upon S cross into. But E is equal to S cross omega. E is equal to S cross omega. S cross we know that S cross E is equal to H upon 2 pi. Omega that is angular velocity. Omega that is angular velocity of the particle. E is equal to S cross omega. Put here value of that is E. E is equal to e raised to minus IE. I put here that is S cross omega minus I S cross omega upon S cross into T is equal to e raised to minus I value of S cross omega to the velocity minus is cross omega upon s cross into t. S cross becomes cancelled. So that is equal to e raised to minus I omega t. That is solution for time part. T is equal to e raised to minus I omega t. Now we have taken psi of x, y, z, t that is equal to u of r bar and t of t. Psi of x, y, z, u of r bar only space variables. T of t and part. Psi of x, y, z, t is equal to u of r bar, t of t. Therefore, psi of x, y, z, t that is equal to psi of x, y, z, both variable, time part and space variable. Psi of x, y, z is equal to u of r bar, only space variables. The solution that is for time part e raised to minus r. U of r bar plus u of t. Psi of x, y, z is equal to u of r bar plus u of t. U of r bar. Psi of x, y, z equal to u of r bar. Only psi of x, y, z is equal to u of r bar t of t. You have taken that is psi equal to only u space variables. T that is time part. Psi of x, y, z equal to u of r bar t of t. Psi of x, y, z is equal to u of r bar space variables. And E, put here that is value of time part. Solution e raised to minus I last one. Psi of x, y, z, t that is equal to u of r bar e raised to minus I omega t, that is solution of time. So we have completed two Schrodinger's equation. First, that is time dependent Schrodinger wave equation. Second, time independent Schrodinger wave equation. In one dimensional case, second, that is in three dimensional case. Now compare these two equations. See. Time dependent Schrodinger wave equation. Minus x cross square upon twice del square psi that is equal to I x cross the outside upon the del square psi plus v psi that is equal to I x cross the outside upon the minus x cross square upon twice del square psi, or that is del square u plus v of psi, that is v of u, that is equal to Ix cross the above psi upon the above t. Time dependent Schrodinger wave equation in three dimensions. And second, time independent Schrodinger wave equation minus x cross square upon twice m del square u plus v of r bar u of r bar, that is equal to e u of r. Time dependent minus x cross square upon twice m del square psi or del square u. Del square pu. That is I s cross def of u upon def of. See difference between these two equations. Minus s cross square upon twice m del square u plus v. Minus s cross square upon twice m del square u plus v of r bar same function u of r bar same that is equal to here is cross above u upon above t here e u of r bar. That means is cross divided by t is nothing but energy operator. Energy operator we have taken E. Same equation, but difference here that is energy operator E, that is here is cross the above u upon the minus minus. Clear? It is clear. These are two, that is Schrodinger wave equations. Minus s cross square upon twice of x square plus v equal to is cross the above u upon the above t and time independent Schrodinger minus s cross square twice x square plus v of r bar u of e u of r. Then, up to this point, we have completed first article, physical interpretation of wave function psi. Second, requirements on wave function psi. Third, time-dependent Schrodinger wave equation in one dimension and in three-dimensional case. Time-independent Schrodinger wave equation in one dimension and three-dimensional case. In time-independent Schrodinger wave equation is called as steady-state Schrodinger wave equation. The next article is eigenvalues and eigenfunctions. Eigenvalues and eigenfunctions. Eigenvalues and eigenfunctions. Now see that. Suppose A is an operator. A is an operator. We know that operator operates on the unit. A, that is operator, simple operator, derivative operator. A is operator. F of x, y, z function, given function. F of x, y, z given function. The operator f of x, y, z, that is given function. Therefore, operator E operates on the function x, y, z produces same function f of x, y, z multiplied by the scalar quantity. E, that is called as scalar quantity. Operator A operates on the function f of x, y, z produces same function multiplied by the scalar quantity. Or in short, A operator operates on the function f that is equal to scalar quantity A. And this type of equation is called as eigenvalue equation. A f of x y z is equal to A f of x y z, or A f is equal to A f. Operator operates on the given function f, produces function itself and multiply by scalar quantity. If we get equation in this form, that means after operation by the operator, if we get that is function f, then this type of equation is called as eigenvalue equation. That means after operation by the operator on the given function, if it produces same function f multiplied by scalar quantity a, then this type of equation is called as eigenvalue equation. Here, A that is operator, F that is given function, and this function F is called as eigenfunction of operator E. Eigenfunction of operator E. In this form, if we get equation, after operation by the operator produces same function multiplied by the scalar quantity E. The production is same function, only multiplied by that is scalar quantity. Then this type of equation is called as eigenvalue equation. Here, f that is called as eigenfunction of operator E, eigenfunction, and small e is called as eigenvalue. Corresponding to operator, eigenvalue of E, A operator. The above x, y, z given function. But after operation, if we get same function, then that function is called as eigenfunction of operator. That is product scalar quantity. It is called as A eigenvalue of operator E. If we get equation in this form, then that total equation is called as eigenvalue equation. Then A operator. Here that is called as eigenfunction of operator E. E small, that is E is called as eigenvalue of E. Now we will see one example. Whether that is given function is eigenvalue equation or given function is eigenfunction for the given operator. Here see that after operation by the operator on the given function, it produces same function multiplied by scalar quantity. If we get equation in this form, then that equation is called as eigenvalue equation for the given quantity. The scalar quantity that is called as eigenvalue. See one example. Suppose that is sine 4x given function. Sine 4x given function. d2 upon dx square operator. d2 upon dx square operator. Sine 4x given function. d2 upon dx square operator. Now operate this operator on the given function. Take that is derivative 2 times. Therefore, d2 upon dx square, that is equal to first that is derivative of sine 4x. It becomes 4 cos 4x. Is it clear? Derivative of sine 4x. It becomes 4 cos 4x. 4 cos 4x. d by dx, first statement. The root of sine 4x, it becomes 4. Sine becomes cos 4x. The root of sine cos 4x. Fine. Now take second limit. D2 upon dx square. The root of this one. D2 upon dx square 4. The root of cos minus sine. Minus sine 4x and the root of this quantity 4. That means 4 into minus 4 sine 4x. The root of 4 cos 4x minus 4 sine 4x. The root of cos minus 4 sine 4x into 4. 4 into 4, 60. But here sine is minus 60 sine 4x. And here operator d2 upon dx square function sine 4x, that is equal to minus 16 4x. Now tell me whether it is Eisenhower equation or not. See there, we have taken that is a f of x y. That is equal to a f of x y. That means after operation by the operator of the function f of x y z, it produces same function f of x y z. Same function is important. After operation by the operator, it produces same function multiplied by that is scalar quantity a. If we get equation in this form, then that equation is called as eigenvalue equation. Scalar quantity that is called as eigenvalue of the operator a. You see that here, d2 upon dx square operator. d2 upon dx square operator operates on the function sine 4x. It 2 times derivative, that it produces minus 16 sine 4x. Here sine 4x, same function. Operator d2 upon dx square. Function here f of x y z, their function sine 4x. After operation produces same function sine 4x multiplied by the scalar quantity minus 16. Therefore, this equation is eigenvalue equation. After operation by the operator, if we get same function multiplied by scalar quantity, then that equation is called as eigenvalue equation. d2 upon dx square function sine 4x, that is equal to minus 16 sine 4x. We get same function after operation multiplied by scalar quantity minus 16. Here, this type of equation is eigenvalue equation. And sine 4x, that is called as eigenfunction. Sine 4x eigenfunction. Scalar quantity minus 16, that is called as eigenvalue of the operator E. Minus 16 eigenvalue. That means if we get equation in this type, that means after operation by the operator, if we get same function multiplied by the scalar quantity, then that equation is called as eigenvalue equation. And scalar quantity, that is called as eigenvalue of the operator. It is to this clear for you. Now we will discuss 2 points. तुमचे कॅमेरे आता ऑन करा, मला मूव करतो, मी काय अर्थ नाही तर हो प्रश्न करतो. पोरांना व्हिडिओ ऑन करून अनम्यूट व्हा.
Hello student, kindly unmute yourself and turn on your video. सगळ्यांनी आपले माइक ऑन करायचे आणि व्हिडिओ पण ऑन करायचा.
सर्वांनी करा व्हिडिओ ऑन आणि अनम्यूट व्हा.
सगळ्यांनी आपले व्हिडिओ ऑन करायचे. फक्त एका व्यक्तीने आज व्हिडिओ ऑन केला, बाकीच्यांनी ऑन करायचा व्हिडिओ, अनम्यूट करायचं स्वतः.
रेकॉर्डिंग चालूच आहे.
पूजा, भक्ती, सानिया, ऋतुजा, ओमकार, निकिता, व्हिडिओ ऑन करायचे.
झाले ठीक आहे.
हॅलो, उद्या बाकी कुठे गेले? बाकी गेले कुठं? आज काय अडचण आहे का कोणाची? श्रद्धा जाधव,
नाही सर.
आज जरा स्टोरी घेतलं ना आपण?
हो सर.
लिहून घेतलं का?
हो सर, घेतलं सगळं लिहून.
पूजा जाधव लिहून घेतलं का?
हो सर.
भक्ती पाटील व्हिडिओ ऑन केला नाही. सुमित मोहिते अरे व्हिडिओ ऑन केला, अनम्यूट केलेला आहे. अनम्यूट करा. मस्के निकिता अनम्यूट करा. यादव, विजय यादव, श्रीधर शिंदे अनम्यूट करा. अनम्यूट करा. सरपाळ, विजय परदेशी, ओमकार पवार अनम्यूट करा. स्नेहल माळी, तुम्हाला सांगायचं तुम्हाला अनम्यूट करायचं. स्नेहल राव, संजय डांगे, ऐकलं सर लेक्चर?
हो सर, ऐकलं.
बरं, काय अडचण आहे का? काय आर्टिकल पण आता पण झालेलं आहे?
नाही सर.
नाही ना? दिशा परदेशी काय अडचण असेल तर मला सांगा, मी आपण त्यानुसार आपण चेंज करू. श्रद्धा जाधव घेतलं का लिहून सगळं?
सर काय नाही अडचण. हो सर, घेतलं.
घेतलं ना?
हो सर, घेतलं लिहून. हो हो.
अवघड वाटते का सोपं क्वांटमला? क्वांटम सोपं वाटते का अवघड?
वाटतंय सर, सोपं वाटतंय.
सोपं वाटतं फक्त आपल्या मॅथमॅटिकल पार्ट फक्त जास्त आहे बरोबर ना परंतु अगदी स्ट्रेट फॉरवर्ड आहे एकदा तुम्ही जर व्यवस्थित वाचत गेला तर काय अडचण नाही हा त्यामुळे
हां
तुम्ही
सर.
मॅथमॅटिकल पार्ट मॅथमॅटिकल पार्ट जास्त आहे म्हणून तुम्ही काय घाबरायचं नाही स्ट्रेट फॉरवर्ड आहे
हो सर.
म्हणजे त्याचा पुढे गेले मग काय करूया आपण थांबूया का थांबूया
हो
तर
सर.
पुढचा तरी
हां सर
तुम्हाला
चालेल.
हा
हाँ
थांबूया
सर.
का जाधव श्रद्धा
हो सर चालेल.
थांबूया
हो.
चालेल मग प्रोफेसर येते त्यांना सांगतो मग घ्या हा
हां हां.
रेड माळी आता दिसते कुठून ते माळी अरे ऑन करायचे हा
हां सर.
काय अडचण का तुझी
नाही काय सर अडचण.
अडचण सांगतो आपल्याला तुम्ही ठेवायला म्हणजे कसं आहे माहिती का फिजिक्सला त्याचा आमची मुलं झाला हा लक्षात घ्या आतापर्यंत तुम्ही अभ्यासाला तुम्हाला बाकी विषय होते कॉमन होते आता कसं आहे तुम्ही ठेवायला म्हणजे आमच्या डिपार्टमेंटचे मुलं झाला हे आमची मुलं झाला त्यामुळे तुमची काय अडचण असेल तर सांगायची वेळेला
हो सर.
तुम्हाला तसं हक्क आहे ना डिपार्टमेंटला बाबा तुम्हाला डिपार्टमेंटला तुम्हाला काय सगळ्या फॅसिलिटी मिळत आहे त्या पूर्वीपर्यंत जमून तुम्ही आता पूर्ण फिजिक्स डिपार्टमेंट मुलं झाला त्यामुळे काय गोष्टी गाव घालायचं वगैरे नाही तुम्हाला सगळं सहकार्याने केलं जाईल
हो सर.
हा तुमच्या एखादं पण मॉनिटर पण झालेलं नाही ऑनलाईन हा नाही ना हा मग त्यांना सांगायचं सर्वांना कोण ऍबसेंट आहे वगैरे त्यांना सांगायचं श्रद्धा होती का
हो
हा
सर.
श्रद्धा
हो सर.
हा मॉनिटर तो ठेवायला द्यायची फिजिक्सची हा आपल्या पोरांना सांगायचं किंवा काय नोटीस वगैरे असतील ती सांगायची हा
हो सर.
सर्वांना सांगायचे हा
हो.
जबाबदारी आपण तुला कोण जोडीदार घ्यायचं असेल तरी घे मुलगा घे किंवा मुलगी घे हा
हो सर.
हा तू रेग्युलर असते म्हणून तुला मॉनिटर केले हा हा
हां.
रेग्युलर असते चालेल थांबूया का मग
हो सर चालेल.
चालेल प्रोफेसर येते आम्ही 5 मिनिटं
हां. काय झालं? बाहेर आलं का काय?
हॅलो, अरे आवाज येतोय का?
हो सर येतोय.
ओके बघा मी 2 मिनिटात जॉईन होतो. 2 मिनिटात एक्झिट करतो हे डिलीट करतो, सॉरी बंद करतो आणि पुन्हा जॉईन होतो लगेच. ओके.